Divergence theorem. Let G be a simple solid region with boundary surface S oriented outward, and let F be a vector field whose components have continuous partial derivatives on some open region that contains G. Then the surface integral over S, F dot ds, is equal to the triple integral over G, the divergence of F dv. Let's try an example. Go ahead and pause the video, try this example yourself, and then resume the video to check your answer. Find the flux of the vector field f of xyz equals z squared I plus yj plus xyk over the unit sphere x squared plus y squared plus z squared equals 1. So the divergence of f, remember, is the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. In this case, the partial of f with respect to x is 0, the partial of g with respect to y is 1, and the partial of h with respect to z is 0. So the divergence of f is just 1. So the surface integral of f dot ds by the divergence theorem is the triple integral over g divergence of f dv. In this case, the divergence of f is just 1, so that triple integral just represents the volume of the solid G. This is just the volume of a sphere of radius 1, which is 4/3 pi times 1 cubed, or 4 pi over 3. Let's try another example. Again, pause the video, try this yourself, and then resume the video to check your answer with mine. Find the flux of the vector field f of xyz equals yz cubed I plus y cubed j plus xz plus sine xk over the unit cube where x, y, and z are each between 0 and 1. Again, the divergence of f is just the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. In this case, the partial of f with respect to x is 0. The partial of g with respect to y is 3y squared, and the partial of h with respect to z is x. And we can write that as x plus 3y squared. So the surface integral over s f dot ds by the divergence theorem is the triple integral over g divergence of f dv, which is the triple integral over g x plus 3y squared dv. This is a triple integral over a rectangular box, so it's pretty straightforward. All the limits go from 0 to 1, and we could do the integrals in any order. Let's do it as dy, dx, dz. Okay, so we're doing the y integral first. So that becomes xy plus 3y cubed over 3, or xy plus y cubed from 0 to 1, which after plugging in the 1, we just get x plus 1. Now we do the x integral, and we get x squared over 2 plus x, again from 0 to 1. Plugging in the 1 gives us 1/2 plus 1, or 3/2. So we just get 3/2 times the integral from 0 to 1 dz, which is just 3/2. One more example. Again, try this example yourself, pause the video, and when you're done, resume the video to check your answer with mine. Let G be the solid bounded by the paraboloid z equals x squared plus y squared and the plane z equals 1, and let S be the boundary of the solid G. Evaluate the surface integral over S, yzi plus xzj plus z squared k dot ds. Here's a picture of the paraboloid, z equals x squared plus y squared. And notice that I labeled a 1 there for the top of the paraboloid where it's intersecting the plane z equal to 1. The divergence of yzi plus xzj plus z squared k is just 2z. Notice that the partial of the first component with respect to x is 0, the partial of the second component with respect to y is 0, and the partial of the third component with respect to z is just 2z. So this surface integral by the divergence theorem is the triple integral over g 2z dv. We'll do this in cylindrical. So theta is going from 0 to 2 pi. R is going from 0 to 1, and z is going from the lower surface to the upper surface. The lower surface is the paraboloid, which is z equals x squared plus y squared, and in polar, that's z equals r squared, and the upper surface is the plane z equals 1. So inside the integrand, we have 2z, and we have to multiply by an extra factor of r, as we always do when we change to cylindrical. Let's do the z integral. That becomes 2z squared r over 2, or z squared r, from r squared to 1. So when we plug in a 1 for z, we get 1 squared r, or just r. And when we plug in an r squared for z, we get r to the 4th times r, or r to the 5th. Integrating with respect to r, we get r squared over 2 minus r to the 6th over 6. We're going from 0 to 1. So we get 1/2 minus 1/6. And the theta integral just gives us 2 pi. So that comes out to 2 pi over 3.